So can I get an example for a heterogeneous mixture? Anybody? Yeah, sure. Oatmeal looks good. Doesn't look the same all the way through, right? It's got oats and not oats and raisins and other stuff. How about another one? Sure, okay, cottage cheese. How about homogeneous? Water is not, it's a pure substance, not a mixture. Sure, shampoo. Some shampoo, for sure, some shampoo. I heard somebody else say something.
Metal alloys?
Metal alloys, sure, yeah. Does anybody know what some common metal alloys? What was that?
Steel.
Sure, steel. Steel's iron and usually carbon and or some other stuff. Brass, bronze, those things are alloys. Yeah, those are good. What's the major difference between a chemical and a physical change?
Composition doesn't change with the physical change, but it changes with the chemical.
What do you mean by the composition does not change with the physical change?
The molecules stay the same on both sides of the equation.
Sure. The molecules stay the same on both sides of the equation. Okay. So something like water, that's a liquid on top of your stovetop that's boiling and it's turning into a gas. So on each side of the arrow, I've got a water molecule, so it doesn't change. And so that's obviously physical change. And the chemical change would be if I took, say, liquid water and I applied voltage to it, electricity, and I separated the hydrogen gas out from the oxygen gas. And then I got two separate things on each side of the equation, so that's definitely a chemical equation in that particular instance. What do we have here? Oatmeal. What was the other thing? Cottage cheese. And we had an alloy, steel, and what was the other thing? Shampoo. What are the three things that indicate a chemical change? Color change. Example?
Heat. Burning something.
Heating something? Okay, so how about like maybe some of you toasted bread this morning, so most likely changed color. Due to heat for sure, but that was a chemical reaction. I heard bubbles. So in the bubbles instance, we're not talking about the addition of heat though. So this example that we had above here where the water was turning into a gas, that wasn't a chemical reaction, and so just bubbles by itself can't be a chemical reaction. With the addition of heat, if I change state, that doesn't count. But if I take, say, baking soda and dump vinegar on top of it, you get bubbles, right? Immediately. There's no heat added, it just happens. That's the kind of bubbles being generated that we're talking about. And what was the last one? No.
Precipitate.
Precipitate. So the formation of a precipitate. So I take, what you need to have is a clear liquid and another clear liquid. And if I mix those two clear liquids together, I get a liquid that has a solid in it. So instantaneous creation of a solid within two aqueous solutions. All right. How about unit? What do we have for a unit? A standard of measurement. So sure, measurement's obvious. What's the standard part got to do with it?
Recognizable.
by,
Like, people understand what you're talking about.
sure, everybody recognizes that when we're talking about a dollar, we're talking about a dollar, or if we're talking about a meter, we're talking about a meter. All right, metric system, why was the thing developed?
Everybody measures the same anyway.
So that first
Same
part,
things.
that definition for this, for the unit is attained. So we get standardization across, it was to make sure all nations were standardized. And we talked a little bit about why the US didn't go. It was basically just about money, right? It wouldn't be a big deal if we switched over to Fahrenheit, but changing all the road signs and whatnot would be very, very expensive. The metric system is based off of what? 10. A kilogram and a milligram are related to each other simply by the number 10. How many times do I have to multiply or divide by 10 to get to that new value? All right, let's go ahead and do these conversions here. So I'm going to convert this decimal or this into decimal format. So what is this 5 here referring to? Okay, so you can think about moving the decimal place by 4, but mathematically, what is it actually doing? So 2.358 is going to be multiplied by 10 5 times. If I multiply it by 10 once, it gets 10 times bigger, right? So the decimal place moves over. So I'm just doing that 5 times. So yes, decimal place moved over 5 times. So 235,800. Do I get to put a decimal there?
No, zeros.
How many significant figures are in that number before we do the conversion over to decimal? 4. So how many do we have written as I have it written up there? 4. Because that decimal place isn't after the 0. If there was a decimal place right here, what would that tell you?
But those zeros are exact.
That person measured that thing and this whatever they were using to measure it stopped on the 0, 0. That's where it actually did. What does this tell you? Oops, let me put that 0 back there.
There's room for error.
No, let's talk about the measuring device again. It stopped on the 100. That this device could measure, this is 200,000, right? In the 100,000s place, the 10,000s place, the thousands place, the hundreds place. But is it accurate enough to measure here? No. This would be, I don't know, measuring the mass of an aircraft carrier. I could care less if it's off by 1,000 pounds. That's how much I care less about that. So these two numbers don't mean anything at all to us. We okay with that? So the person simply doesn't know. These are completely inaccurate. It could be zeros, it could be 9 nines. We don't know because the scale only measured these 4 most significant numbers and these don't count. Okay, scientific notation on the other one, what do we do?
To move the decimal back.
So whenever we write scientific notation, what format does the number take? One actual number, not a 0, and then a decimal place, and then everything else you have to write. That's how it's written. So I write 6.5895, and then I determine what I need to do with my 10 to the whatever. And how many spots did we move the decimal place this time? 4. So I'm going to write times 10, and why is it 4 and not -4? Yeah, because I need to make that number there, the scientific notation number, bigger by 4 orders of magnitude. So I need to multiply it by 10 4 times to get it back up to that 65,000. Okay, this next one. So I've got a 10 to the -3, so what am I going to do with this? So I'm going to go 0.0058994. There's not a decimal place there. Okay, so again, we have 4 significant figures with this. What are the 3 zeros in front of the 5 used for? Placeholders. The entire medical field is going to that 0 in front of the decimal place. mathematically it doesn't do anything. So the zero I'm talking about is this guy right here. So mathematically that you could have that zero there or not have that zero there, but the entire medical field wants this zero here. And so make sure that you have a zero here if you've got a decimal place. So there are three completely insignificant figures with this, but these four are all significant. Okay, how about this last one here? What do I write? -4? So when you're looking at this, I've got this this 9.23 times 10 to the -4. And what we're saying is this number right here, this 9.23, when does this number equal this number? What would I have to do to make those two numbers equal to each other? If I multiply this number by 10 to the -4 or divide this number by 10 4 times, then those two numbers are equal to each other. That's all scientific notation is doing for you. This number here, or let's go with this one. This is a small number, right? 6.5. This is a big number, 65,000. How can I make 65,000 and 6.5 equal to each other? If I multiply 6.5 by 10 4 times, then they're equal to each other. That's another way to think about that. Okay, let's convert this 285 inches into meters. So I'm going to start off with 285 meters. That was what I was given. So how many significant figures do we have? 3. We're not going to have to worry about significant figures for the rest of this problem because everything else that we're going to use is going to be an exact quantity or definition. So what I need to do is go from 2.54 centimeters equals 1 inch. That's the only way. I need to use that conversion to get myself over into the metric system. No other conversion is going to be allowed. Where are we with that? Why? It's the only conversion that goes from the English metric system that's distance related that has the word exact next to it. So that reason that's important to us is 1 meter is what do I need? 100 centimeters. So do I have to worry about any significant figures with this here? Is all of a sudden my significant figure number for this 1? Uh-oh. Yeah, thanks for catching me on that. Inches. So get rid of that. And I'll put 12 inches and 1 foot. So is there any, is my significant figure number now 1 because there's a 1 right here? What significant figures have to do with? Second?
The measurement?
Okay, what about the measurement? Definitely about the measurement.
How exact the measurement number is.
How accurate your measurement is. So we've stated here that somebody measured this 285 inches and they measured it 285. So there's 3 significant figures here. So what we're saying is I have three numbers of accuracy to this 285. It doesn't say 285.0, which means they didn't bring the decimal place out on whatever they were measuring with to the 0th point. They only know it to the final inch. They don't know it to the 10th of an inch. Okay, so I only know this 3 digits of accuracy. How accurate is this? It's exact. It's 100% accurate. There's 0 error whatsoever. We okay with that? This is 112. So do I have to worry about this being inaccurate? So then I don't have to worry about significant figures with this at all. We okay with that? So the reason this one has significant figures is, do you think that this thing that they measured was exactly 285 inches on the spot, dead even? This number here, this decimal place is a decimal place, and what number could it be after that? It could be a 0 all the way up to a 9. I don't know because they didn't measure it. I don't have that problem over here. There is no wiggle room for 12 and 1. It is 12 and 1, period. It's never going to be 12.1. It's never going to be 11.9. It's only ever going to be 12. So using this, I don't have to worry about the significant figures because There is no inaccuracy in that conversion. So I skipped it, but why did I put the inches on the bottom, the 12 inches? Yeah, I need to cancel this inch up here in the numerator, right? So what has to go right down here? Oh, geez, no, no. I messed this all up. Why didn't somebody say something? 1 inch and 2.54 centimeters. Is that better?
Yeah.
All right, thanks. So what has to go down here? Centimeters. And what do you want to put up when we're trying to get to meters? Meters, right? Everybody okay with that? 1 meter, 100 centimeters. So now the centimeters are gone. The only unit I have left is meters. The way I like to do the unit conversions for the metric system is whichever of the two units is the smaller or is the larger unit, I give it a 1. And then what I say is, this is 1 meter. How many centimeters fit in 1 meter? 100 centimeters make up 1 meter. As opposed to, what's the other way I could write that? I could write 0.01 meters and 1 centimeter. Not quite as easy to see. So what we're saying is 0.01 of a meter is equal to 1 centimeter. So 100th of a meter is 1 centimeter. I just always think it's easier to say it takes 100 of these things to equal this one thing. So the smaller thing is usually, or the smaller unit is the thing I make the bigger number. Okay, so what do we got here? So 285 times 2.54 divided by 100, and I got 7.239. Is that good? No, that's not good. What's wrong with my answer? I have too many significant figures. How many do I get to report? 3. I reported 4, so what should I report? 7.24 meters. Since that 9 is a 9 and 5 or greater, then I'm going to go ahead and round up that 3. All right, so we're going to go 24 feet per second, and we're going to go into miles per hour. All right, so 24.5 feet per second. And I'm going to do the time unit first. It totally doesn't matter which one you do first, but I'm just going to do the time one. So it'll be 60 seconds is 1 minute. So then my seconds will cancel out. And then I'll go 60 minutes is 1 hour. What would happen if I stopped and did the math right now? What would my units be? Feet per hour? Okay, I don't want feet per hour. So I'm going to get rid of this feet by putting it down here. And I can convert right into miles. So for every 1 mile, it's 5,280 feet. So each one of those unit conversions is exact. Are we okay with that? Alrighty, so the feet unit here cancels out with that feet unit there. And then I get miles per hour. What is this? 24.5 times 16.7? And is that answer okay? 3 sig figs, 3 sig figs? All right. We didn't start talking about the density stuff yet, but it's okay. When we're using the railroad track stuff, the only thing you need to know is what the answers unit is. And so what are we looking for here? We're looking for volume, and the only unit up here that's a volume unit is a milliliter unit. So I'm going to take the 2 numbers I have and set them into that railroad track thing to cancel out, so I get milliliters, and that's the only unit I get. So the way to do that is 0.92 grams and milliliters in the numerator. Is that okay? Asking if that's okay is like saying 1 meter is 100 centimeters. 100 centimeters is 1 meter. Those are both okay, right? They're the exact same thing, so we don't really care. So in this number here, this 0.92 grams per milliliter, what isn't being shown? There's a number not being shown. What is it? Not a 0. Oh yeah, we should put a 0 there, sure, yeah. We're not talking about that one. A 1. This 1 milliliter. What this is saying is 1 milliliter of this substance has this mass. Or this mass of this substance would give you 1 milliliter of volume. So that's why it's okay to flip this whole thing over. I could put the 1 right here if you want, but it's a 1, so it doesn't really count in the calculations. But why did I put it upside down like that in the first place? I need milliliters, and I need milliliters to be in the numerator of my answer because I want milliliters for my answer. And if I would have written 0.92 grams divided by milliliters, my milliliter unit would have been in the denominator, and it would have got an answer that was upside down. The whole answer would be upside down. So in this case, all I need to do now is get rid of the grams, and I have a gram numbers, and it was 355 grams. So this gram cancels out with that gram, and what do I have left? Milliliters. That's it, right? So I got 355, and then divide it by 0.92. No, divided by 0.92. There we go. So I get 385.87. Is that okay? No. What do I get to write? Nope. 390. 390 milliliters. Do I put a decimal place right here? What happens if I put a decimal place there? It means that 0 is, we're sure about that 0, and we're not sure about that 0. We're only sure about the 3 and the 9 because we were only given 2 significant figures. So I said when we were talking about significant figures that this would be kind of a pain in the butt, but we'll just keep doing it, and then you'll like, oh, okay, I get it now. So don't worry about it. We'll just keep doing it.
So how come you chose two significant figures if 355 is 3? So how did you decide which one?
Whichever number I'm using has the least number of significant figures, that's all I can include in my answer. So you're right, I had 3 with the 355 and 2 with the 0.92, but since the 0.92 is only 2, that's all I get to use. Okay, any questions?